Hello, this lecture is going to focus on sigmatropic rearrangements as well as the chemistry of fission and conjugation. First, we'll talk about sigmatropic rearrangements. This is one in which a sigma bond is formed at the expense of another sigma bond, and this happens by electrons moving around in a ring. We have the loss of one pi bond is the gain, or sigma bond is the gain of another sigma bond. The transition state looks like this on the right, where we have three carbons and 3 carbons on each side of the molecule that stay in place. So we have 4 sigma bonds that don't change, and then we have sigma and pi bonds that do change, and they're in this dotted area in the middle. There are many kinds of sigmatropic reactions, but we're going to focus on the 3-3 rearrangements. This means that there are 3 molecules between the atoms that are rearranging. There are 3 carbon atoms between the molecule that's rearranging. In this example that I've shown you, the starting material and the product have the same energy, and that's because they're the same molecule, but they can still undergo rearrangement. But for a reaction to occur, we want the product diene to be more stable than the starting material diene. So let's look at how we can do that. First, let's define some reactions. When all of the atoms are carbon atoms, then this is a Cope rearrangement. In a Cope rearrangement, we take a diene and move the electrons around in a circle again. And we get to our new diene. Now, why does this reaction work? It's because of this comparison of pi bonds. Notice that both pi bonds in the starting material are singly substituted, whereas in the product we have a singly substituted pi bond plus a doubly substituted pi bond, and we know that this doubly substituted pi bond is more stable than a singly substituted pi bond, so that's why in this equilibrium between the starting material and the product that we favor the product. Notice that I've just rearranged these molecules so that they're in a linear geometry. You should be able to convert starting material and product, whether these are given to you in a cyclic rearrangement or as a linear zigzag. When oxygen is involved, then we have something called the Claisen rearrangement. The Claisen rearrangement, again, you have 3 bonds moving around a ring, and we have switched one sigma bond for another. So what's the driving force of this reaction? We have 2 pi bonds in our starting material and 2 pi bonds in our product. Well, it's this carbon-oxygen pi bond which is more stable than carbon-carbon pi bonds. The carbonyl carbon is more stable of a pi bond than the carbon-oxygen pi bond because oxygen is a more electronegative atom, and that means its pi orbital is going to be lower in energy. Whenever you have a more electronegative atom, that orbital is going to be lower in energy than the less electronegative equivalent. So that's why the product is favored in this case. Let's try a few examples where we draw the products of the reactions. I'm going to ask you to pause your video and see if you can draw the product of this first reaction. Here our molecule's already set up in a cyclical rearrangement, so we can draw our electrons going around in a ring without rearranging the molecule. and we get this following product. Not only do we have the more stable carbonyl bond, but also our pi bond is equally substituted to the original pi bond. So we're not gaining anything here, but we're gaining something by forming that carbonyl pi bond. Now I'm going to ask you to pause your video and see if you can figure out the product of this cope rearrangement. Welcome back. Now this time we don't have our carbons in a cyclical rearrangement or cyclical arrangement, so we need to move our atoms around so we get this methyl group in position for our reaction. Now we can move our our pi bonds and sigma bond around in a ring. And we see that this product is formed. Okay, I want to do one more practice with you. See if you can figure out the product of this reaction. I want you again to pause your video and give this a shot. What's going to clue you into this being a rearrangement reaction is that you have two pi bonds. The oxygen atom's telling you that this is going to be a Claisen rearrangement, not a cope. But we have to set the molecule up in a cyclical structure before we do our mechanism, or else we're going to get messed up with our product. There, if you didn't get this, pause your video again and see if you can get to the product from this stage. Now, it's a little awkward with the bond angles of the alkene, but this molecule will stretch out nicely once the cyclization is finished. Notice that the driving force for this reaction, again, is the formation of the carbonyl, which is a stronger pi bond than your carbon-carbon bond. The carbonyl is a stronger bond than the carbon-carbon pi bond. Next, we're going to switch gears and talk about UV-Vis spectroscopy. When we talk about UV-Vis spectroscopy, we want to think about what happens to our carbons and pi bonds when they're treated with light. So let's fill the molecular orbitals for butadiene in this case. When butadiene is irradiated with light, then we get the excitation of one of our electrons to the third molecular orbital. And this electron is going to decay over time to the second orbital, reforming the first. So this is going to happen either vibrationally or with fluorescence. Think about when you are in the summertime and you're wearing a white t-shirt versus a black t-shirt. You're going to get warmer in the black t-shirt, and that's because your black t-shirt is absorbing more light than your white t-shirt, which is reflecting light. Your black t-shirt is not fluorescent. We know that because if you put your black t-shirt under a UV light, then it shows nothing. So that means that the light that is absorbed from the sun is going to vibrationally decay. And that vibrational decay is what gives you the warmth sensation, and that means if you want to stay cooler in the summer, then wear white. Now let's take a look at three molecules with extended conjugation lengths, starting with butadiene. Let's populate those molecular orbitals. And what you can see from this diagram is that the gap between the HOMO and the LUMO is becoming shorter as we get to increasing conjugation. With enough conjugation, you can get this energy gap small enough that you get light absorption in the visible region. These three molecules that I showed you are going to absorb in the UV region with absorption values of, let's see, 217 nanometers, 258, and 290 nanometers. So this is showing you that as you increase the conjugation length, you decrease the energy gap. So a smaller number of wave numbers is a larger energy. So we're actually going from high energy on the right to low energy on the left. So let's add this line for increasing energy. One example of a molecule that is so conjugated that it's colored is beta-carotene. And this is the chromophore that's found in many foods that are colored red or orange, including carrots. And carotene is broken up by your body and used in the pigments in your eye to absorb light. And it's responsible for giving you good night vision. So it's important to eat your carrots if you want to have good night vision. There was a scientist who studied the chemistry of vision, and he did this by attaching a molecule that's conjugated to the protein opsin. And notice that in this protein we have all trans bonds except for this one, which is a cis bond. That scientist found that when you absorb when this molecule absorbs light, that this pi bond changes from trans to cis, or from cis to trans. And that when the absorption of light changes our photoreceptors by undergoing this cis to trans change, then our photoreceptors initiate an enzymatic reaction that causes the release of calcium ions, and that blocks the pathways of sodium, and the reduction in current caused by this calcium ion blocking causes nerve impulses in the brain to change, and that changes our vision. Now we're to the end of our chapter, and let's look at a summary of what we need to know. We need to know conjugation and the effect of light absorption on on the effect of conjugation on light absorption. We need to know our then molecular orbitals. We need to know our reactions, including the conjugate addition of hydrobromic and hydrochloric acid to a conjugated diene, keeping in mind that we have no rearrangement at lower temperatures or minimal rearrangement at lower temperatures, and at higher temperatures we get the conjugate addition product. We need to know our Diels-Alder reaction, and where a diene reacts with a dienophile. A lot of times you'll see a dienophile with electron withdrawing groups because this promotes the reaction to occur by giving us a LUMO at a lower line energy, which gets it closer to the HOMO energy of the diene. The diene often has electron donating groups to raise its HOMO energy to meet that of the LUMO, and the diene often has a linker group to keep the diene in the S-cis conformation because that is more reactive than the S-trans conformation that the molecule would be in most of the time if it didn't have this fusion element. We also know now the Cope reaction, where we have a hexadiene that rearranges to form a different hexadiene. We want to be careful of which way the reaction is going, and we want to favor the side of the reaction that has more substituted alkenes than less substituted. And lastly, we have the Claisen reaction, where we have a six-membered, part of a six-membered ring. It's not a six-membered ring because we don't have a bond here, but we have the movement of 6 electrons around a ring in a transition state to change a carbon-carbon bond into a carbonyl bond. And that carbonyl bond is lower in energy, and that's what drives this reaction forward. So that's all for chapter 16. We'll start chapter 17 next week.